Hey guys, welcome back. Today we're going to be talking about seawater and particularly ocean current. So let's talk about what makes up seawater. So seawater is a solution. We've been talking about solutions. It is 96.5% water and 3.5% dissolved salts. Now, most abundant salt is sodium chloride, which is just your basic table salt. But we have some other salts. So when I say salt, I'm not talking merely about table salt. Salt is a general term for a metal and a nonmetal when they are bonded together, and we'll definitely go more into that when you get into chemistry. But we have chloride salts, we have magnesium salts, we have calcium salts, potassium salts, sulfate salts, and that all makes up parts of seawater. So what are the properties of seawater? So seawater is unique from our water that we have on every day. So let's talk about what makes it unique. So salinity, all right, is the measure of the amount of dissolved salts in seawater. All right, and we express this as grams of salt per kilogram of water, which works out to be parts per thousand. Remember when we were talking about river water and surface water, we were talking about parts per million. Here, when we get to seawater, we're talking about parts per thousand. So, for example, if we have 35 grams of salt dissolved in 1,000 kilograms of water, that's a 3.5% salt solution. All right, seawater on the whole is about 35 parts per thousand, or 3.5%. Seawater also contains dissolved oxygen. A lot of you complain about when the water comes out of my tap that it's cloudy. That's the dissolved oxygen in it, or dissolved nitrogen and carbon dioxide. You need that, and it happens naturally with waves and everything. Also, nutrients, including nitrates, phosphates, and silicates, are key, and that comes from fish poop, fish vomit, dead animals, all sorts of things give those nutrients to the water. So the salinity around the world is not the same. So the salt that the saltwater makeup on the coast of the Atlantic Ocean is not the same as in some other areas. And so you can look at this map and see the differences. So subtropical regions, in the tropics, evaporation exceeds precipitation, so the salt levels are higher and can be up to 37 parts per thousand. All right. Tropical regions, there's a lot of precipitation, so the salinities are lower. Polar regions, you have a lot of melting sea ice, so you again have lower salinities. And the lowest salinities occur where rivers meet oceans. So if we were to think about where the Cape Fear River comes out in North Carolina, where the Mississippi River comes out, that lowers the salinity. So where are the sea salt coming from that is making that salty? So the salinity of ancient oceans is similar to what it is today, but the salts come from dissolved volcanic gases and the weathering of rock. So as rock weathers, remember, salt is just makeup of rock. So as it weathers, it goes out into the ocean, and also volcanic gases. Remember, there's volcanoes under the ocean, Mid-Atlantic Ridge. That's all giving off gases that have salts in them. So what do we do? How do we remove sea salts? So although salts are continually added to the seawater, the salinity does not increase, which means that some of it has to be removed. All right. So salts are being removed from the ocean at the same rate they are added. All right. Some precipitate near arid and coastal regions. Salty spray droplets are picked up by the wind and carried inland. And then marine organisms remove the salt from the seawater to build their shells, their bones, and their teeth. So when you get that crab shell, it is made up from part of it is made up from the salt in the ocean. So what are the properties of seawater? So one, it is very different than freshwater. Freshwater has a density of about 1 gram per centimeter cubed. But salt is heavier than water, all right? So the density of seawater is greater. So the more salt, the more dense. And temperatures affect density. Cold water is more dense than warm water, just like air, and we talked about that in middle school, all right? Because of salt, the freezing point of seawater is -2 degrees Celsius. This is called freezing point depression, and there's a perfect little calculation you can do in chemistry to calculate this. But Pure water has a freezing point of 0 degrees Celsius. Seawater is -2 degrees Celsius. And we have a lovely density image here that shows you how this water separates, with the blue, cold, salty water at the bottom. All right, absorption of light. So the intensity of light, or how bright the light is, decreases with the depth. So the further you go down, the less light you see, which is, I'm sure for many of you are like, well, nada. Okay, and that is because water absorbs light. All right, so the light from the sun can only penetrate about the upper 100 meters of the seawater. And if we can think about how the ocean is a couple miles deep, after about 100 meters down, you can't see any light. Photosynthesis, which we know is necessary for the survival of most life, only occurs in the top 100 meters of the ocean. And this is why we have what's called ocean layering. Temperatures in the ocean range from -2 degrees Celsius at the poles to 30 degrees Celsius in the equatorial regions. But the average surface temperature is about 15 degrees Celsius, which is slightly cooler than like a 72-degree day. So 25 degrees Celsius is a 72-degree day. Temperatures, of course, decrease with the depth. And deep ocean water, even in the tropics, is always cold. And we have a lovely image here that shows you the temperature of the water as you go down in depth. So the ocean can be divided into 3 layers. The first is the warm sunlit surface layer. That's about 100 meters thick. This is the area where light reaches it. Then you have the thermocline, which is a rapidly decreasing temperatures with the depth, okay? And then you have cold and dark, where the temperatures are near freezing. The first and second layers are absent in the poles because it's all cold there. Layering is caused by temperature differences. Cold is more dense, so it sinks to the bottom. Warm is less dense, so it rises to the top. So let's talk about water masses. There are 3 water masses that account for most of the deep water in the Atlantic Ocean. There's the Antarctic bottom water, temperatures below 0 degrees Celsius, they're coldest and densest in all the oceans. The North Atlantic deep water, this forms offshore from Greenland and is less dense than the Antarctic bottom. And then we have the Antarctic immediate water. This is the less dense of the 3. And if you look at our lovely image here, that covers the 3 water mass layers. All right, ocean movement. So how does the ocean move? So first, what's very clear to us that you can see are the waves. And this is a rhythmic movement that carries energy through space and matter. And in this case, it's the ocean water. It's mainly made by wind flowing over the water surface. As the wave passes, the water moves up and down in a circular motion and then returns to its original position. All right. Only the energy moves forward, not the water. Okay, the water is moving in circles. So the water is not actually moving forward, it's going up and down, but staying in the same location. So let's look at wave characteristics. The highest point of a wave is called a crest, and the lowest point is called the trough. The vertical distance between crest and trough is called the wave height, so the vertical distance. The distance from crest to crest is called the wavelength, all right? And the wavelength determines the depth, okay, which means the wave base half the wavelength is the wave, determines the depth the wave disturbs the water. And wavelength determines the wave speed. As the wave speed increases, the wave speed increases with wavelength. All right, so the wave height depends on 3 factors: the wind speed, the wind duration, and the fetch. And the fetch is the expanse of water that the wind blows across. Okay, so if you think about sending your dog to fetch a ball, the greater the fetch, the greater the wave. All right, hurricanes blow over vast expanses of water, therefore creating larger than average waves. All right, breaking waves, so the breakers. This is where the ocean waves lose their energy due to friction with the ocean bottom. The waves slow down, the wave crest catches up with each other, and the wavelength decreases. And this is where you see that white part of the wave right as it reaches the shore. And this is called, of course, where the crest collapses is called the breakers. All right, tides. We're going to be really looking at this in labs. This is a periodic rise and fall of the sea level. The highest level is called high tide. The lowest level is called low tide. It is a daily cycle of 24 hours and 50 minutes. The tidal range is the difference between the high tide and low tide, and it ranges from place to place. And the greatest tidal range is in the Bay of Fundy with a 15-meter difference. So what causes the tide? It is the gravitational attraction between the Earth, the Moon, and the Sun. The Moon causes tidal bulges on opposite sides of the Earth, as you can see in this little diagram here. And we'll be looking at that some more with a lab. All right, now what is the Sun's influence on the tide? So lunar tides are twice as high as solar tides because the moon is closer to the Earth. And depending on the phases of the moon, solar tides can either enhance or diminish the lunar tides. So we have neap tides is when the moon is in its first or third quarter. And this is when the sun, moon, and the Earth are not aligned. And this results in high tides being lower and low tides being higher. Spring tides are when the moon is either new or full and the sun, moon, and Earth are aligned. And the high tides are really high and the low tides are really low. All right, ocean currents. We have two types of currents. We have density currents, and this is caused by differences in temperature and salinity of the ocean water. And then we have surface currents, and this only affects the upper few hundred meters of the ocean, and they can move as fast as 100 kilometers per day. And surface currents are driven by the Earth's global wind systems, and they follow the same path as those wind systems. Gyres. So the continents deflect the ocean currents so that closed circular movements occur, and these are called gyres, as you can see in the image below. There are 5 major gyres: North Pacific, South Pacific, North Atlantic, South Atlantic, and Indian. Upwelling. Ocean water also moves vertically. The upward motion of the ocean is called upwelling. Upwelling waters are cold, and they mainly exist off western coasts of continents. And they are rich in nutrients, which support abundant populations of marine life.